Hello, everybody again. Today, it's our first speaker of our Wombat workshop, Professor Javier Peña. So Javier is a Bajaj Family Professor, Chair Professor of Operations Research at the Tepper School of Business at Carnegie Mellon University. And Javier's research interests are in theory and algorithms for convex optimization, as well as optimization models in finance and machine learning. So Javier has been at Carnegie Mellon for a long time now, and he did his PhD at Cornell, and then he had a postdoc at the Mathematical Sciences Research Institute at Berkeley, and then since then he has been at Carnegie Mellon University. So I guess Javier, please go ahead.
Thank you, Vera. So before I dive into the talk, I want to thank several people. So Min, Vera, for inviting me to take the inaugural talk in this workshop. This is the first time that I'm participating in this workshop. So it's quite an honor to be giving the opening talk, and in particular a keynote address. It was very nice to see that Nam, one of our former students, is also involved with the organization. So it's nice to have some friends in the audience. I also want to just make a quick comment about Asen Donchev. I'm saddened, like many of you, about losing him. I learned about it actually from the correspondence that I received for this workshop. Asen, I'm sure that he was a very popular person, a very popular guy, and such a special person with so many qualities. I know we are all going to miss him. Unfortunately, I cannot make it to the memorial service because of the memorial session because of the difference in time zones. But I wanted to make a few remarks about him. So let me now switch to the talk. The title of my talk is Perturbed Fenchel Duality and FirstOrder Methods. This is joint work with one of our former students at Carnegie Mellon, David Gutman, whom I noticed is actually scheduled to talk a little bit later today. He may be already in the call. I have organized the talk in a few segments. So, ideally, the segments are going to be increasingly get a little bit more technical. So I will deliberately emphasize the first two segments so that if I lose you, at least you get the main gist of my story. So let me take it away. Okay. So to start, I want to start with some motivation. So as Vera indicated, I spent most of my waking hours thinking about convex optimization. And I want to start with these two very popular formats of convex optimization problems that we encounter in many applications. In particular, these two formats are very, very pervasive in machine learning. So the constraint format where we are optimizing a convex function f over some convex set C, and often the set C has some simple structure. It is a box or it is a simplex, some kind of particular simple structure. I'll make a little bit more precise what we mean by simple. Another format that is also very, very common in many data science models is this composite minimization, where we have, rather than having a constraint, we have the sum of two terms, f of x and psi of x. Typically, f is some kind of smooth component, and psi is some kind of regularization component. So the standard example, the iconic example, is the Lasso regression model, where the second term psi is some L1 term. Here, f and psi are convex, and psi, the second term, has some simple structure that I will try to make more precise in a moment. The composite format naturally subsumes the constraint format by taking the case when psi, the second component, is just the indicator function of some convex set. Okay, so in some way, the composite format is a bit more general. So the main idea of my preamble is these iconic algorithms for convex minimization that I'm sure most of us have seen, if not all of us have seen, maybe we have seen them recently. So these are some iconic first order algorithms for the constraint case for minimizing a function over a closed convex set C. So here, a little bit of notation, pi C is going to denote the orthogonal projection onto the set C. So one of the oldest and most versatile methods to minimize a function over a convex set is the subgradient method. This is a method that makes very, very weak assumptions about my problem. The objective function doesn't even have to be differentiable. And the method is very simple. We pick a subgradient and then we update by taking a direction in a step towards the negative, in the negative direction of the subgradient, and then projecting on the set C. So that's how the iterates are updated. That's the projected subgradient method. If the function that we are trying to optimize is differentiable, then this actually becomes the projected gradient descent, one of the, again, the oldest algorithms, maybe one of the first algorithms that we teach in any kind of optimization course. And the projected gradient descent is we take a direction we take a step in the negative direction of the gradient and then project on the set C. So that's projected gradient. And then we have conditional gradient. Conditional gradient is a little bit different. What we do instead is this requires an assumption that we are able to compute this minimizer easily. So this is usually called a linear oracle assumption about the set C. Rather than moving a step along the gradient, we first compute the minimizer of this linear mapping on C. Let's call that S. And then we take a convex combination from the current iterate in the direction S. So this is just a convex combination between the current iterate and this SK that optimizes this linear mapping. So these are three iconic algorithms that, again, I am certain most of you, if not all of you, have seen probably recently. Let me mention a couple of other iconic algorithms, this time for the composite minimization problem. So the one where we have these two components. And here, by the way, in the previous case, you can see that the simplicity of the set C is reflected in the fact that in the algorithms, I should be able to compute this projection easily. And that is indeed the case if the set C is a simple enough case. For example, the simplex or certain polytopes allow you to project easily. Here, the assumption about the second term here is that we can compute this so-called proximal mapping. So the proximal mapping is defined as this mapping that for any G computes the minimizer of this term here. Okay, so where we take this this term of the Euclidean distance from G squared and we add psi. So the function size should be simple enough so that we can compute this minimizer. Again, for certain functions, often some of the examples that we see in data science, like the L1 minimization, this is indeed a computable mapping. Just a note here, if the function psi is the indicator function of C, then the proximal mapping is identical to the projection mapping. And then the proximal gradient is something that has a flavor very, very similar to the projected gradient. So again, we move in, here is the projected gradient, right? We project it. Here, instead of projecting, we compute the prox mapping, okay? So this is the proximal gradient for this problem, for the composite problem. And then there is this tweak on the proximal gradient. This is called the fast proximal gradient. The key difference between the proximal gradient and the fast proximal gradient is the following. If you look closely at the second line here, the prox is computed from the point xk, and we compute the gradient at xk. Here in the fast proximal gradient, the update on xk is computed from a second sequence yk, and the gradient is evaluated at yk. And yk in turn is updated according to some kind of momentum term on X. So this is the fast proximal gradient. It's an algorithm that can be seen as a tweak of proximal gradient. This can be traced back to Nesterov, then Beck and Tabul wrote a paper that is very popular. It's called the FirstOrder Method, that is essentially this kind of fast proximal gradient. And then Nesterov also wrote a paper a few years later where he proposed a similar kind of algorithm, essentially a very similar algorithmic scheme. Now, here is essentially the key punchline of what I'm going to do over the next 50 minutes. So, and I want to maybe share a personal note. Typically in my convex optimization, in my graduate level convex optimization course, I cover all of these algorithms. If you have taught convex optimization, chances are you have also done the same thing. And then it dawned on me one day that I would come to class and teach the subgradient algorithm. Then I would come to class the next lecture and teach the gradient descent algorithm. And maybe another week, I would teach conditional gradient. And then eventually I will teach the fast proximal gradient. And then all of these algorithms seem to have some elements in common, and the convergence rates that can be shown based on some suitable assumptions of smoothness and choices of step sizes are as indicated in this table. The subgradient method makes very weak assumptions and converges at this relatively slow sublinear rate. Okay, so to get after k iterations, I am about 1 over square root of k away from optimality. The gradient descent, conditional gradient, and proximal gradient, they all have sublinear convergence that is like 1 over k. And then the fast proximal gradient for the same class of functions has this much faster convergence, 1 over k squared. So there are so many algorithms and so many convergence rates. Can they all be unified in some way? Can they all essentially be seen as in one single approach? Can we get all those convergence rates in some way with one single stroke? And the answer that I want to claim is that yes, that can be done. And David and I did it, and it can be done. And the essence is to proposed a certain idea that we coined perturbed Fenchel duality. Perturbed Fenchel duality. So that is the idea of my talk. More precisely, this is the theme that I will try to develop again over the next 40 minutes or so. We will detail a first order meta algorithm. So it's a meta algorithm because it's actually a class of algorithms, and the meta algorithm satisfies a perturbed Fenchel duality property. The meta algorithm includes as special cases, essentially the algorithms that I have described so far, and even another one. So it contains as special cases the conditional gradient, proximal gradient, fast proximal gradient, proximal subgradient, and even one algorithm that is called the universal proximal gradient, that in some way is the most generic one. The perturbed Fenchel duality property will yield, and I will try to make the point for that, will yield concise derivations of the convergence rates that we know for all of these algorithms, of the best convergence rates that we know for all of those algorithms. So that is the essence of my talk. If, God forbid, I lose you now, if you made it this far, at least I accomplished something today. So, of course, I very much hope that you stay with me, because the best part of the talk is yet to come. But this is the preamble that I hope at least I communicated so far. So let me move to the second segment of my talk, that is in some way the main idea here, which is what we coined perturbed Fenchel duality. This naturally, as its name suggests, is a version of Fenchel duality. So let me review real quick the Fenchel conjugate. The Fenchel conjugate is this very, very fundamental construction in convex analysis. if we have a function from Rn, an extended valued function defined on Rn, the Fenchel conjugate of f is this function f star that we define here. It's essentially a dual object of f. And there's a very pretty duality that we have between f star and f. In particular, we have this inequality, the Fenchel-Young inequality that pretty much holds by construction. If we take a point x, a pair of points x and u in Rn, f star of u plus f of x is always greater than or equal to ux. And the equality holds precisely when u is a subdifferential, is a subgradient of f at x. Just a quick recollection here for some of you, if you're a little rusty on your convex analysis, this is the subdifferential, right? It's the collection of essentially subgradients. The subgradients define the affine minor ends of f around the point x. So that's that. So that's the Fenchel conjugate. And then the Fenchel dual is the following. So Fenchel duality is the following nice duality relationship. If we think about our composite problem, minimize f of x plus c of x, the Fenchel dual of that problem is this problem where we it's a dual problem where the objects that define the dual are f star and psi star. Okay, and this is kind of maximization. It's very easy to see that the case of, say, linear programming duality is a special case of Fenchel duality. Fenchel duality and Lagrangian duality are very closely related to each other. The two problems, the primal problem and the Fenchel dual, have this immediate weak duality relationship. If we take a primal point and a dual point, if we take the primal objective, right, that is always greater than or equal to the dual objective, which is a simple way of expressing that is, if we take f of x plus psi of x, the primal objective, and then add f star plus psi star of minus u, this is the negative of the dual, that's always greater than or equal to 0. So in particular, if we find 2 points, x bar and u bar, that reverse the inequality here, right, maybe with an epsilon, then that must be, those 2 points necessarily are epsilon optimal, meaning if this is less than or equal to epsilon, since we also have the weak duality, then both x bar and u bar are such that for the primal problem and for the dual problem, their objective values are less than epsilon from optimality. Okay, so this is kind of key, and this is very much suggestive of what we are going to do. So this is Fenchel. So this is Fenchel duality. This is very classic. And then what we suggest is to consider a perturbed version of Fenchel duality. So the gist of my story is, I will show you in a moment a first order meta algorithm, and I will argue that that very, very generic first order meta algorithm generates sequences xk, uk, such that this kind of perturbed Fenchel duality holds. Okay. If we didn't have the perturbations, if dk was equal to 0 and delta k were equal to 0, if both of them were equal to 0, the iterates that we are generating would have to be optimal. The fact that we have some perturbation here means that essentially they're going to be near optimal. So here, again, what I'll detail is that the first order meta algorithm generates those iterates where the perturbations here, dk and delta k, are both converge to 0 as k increases. So a little observation here. This follows just by applying the definition of the Fenchel conjugate. If we evaluate f, the conjugate of f at uk and the conjugate of this perturbed psi at minus uk, this is greater than or equal to minus f of x minus psi of x minus dk of x for any x. This is a very simple calculation, and it just follows from the definition of the conjugate. So if we put together the perturbed Fenchel duality and this straightforward inequality, we get this inequality you see at the bottom here, the inequality at the bottom here, which essentially says, well, for any point x, whatever my iterate xk is, that objective cannot be much bigger than the objective of x here. So this is going to be the crux of proving the convergence of algorithms, because again, by putting together those inequalities, we get that inequality here. Okay, so let me move to my third segment, which is the first order meta algorithm. So again, the gist of my story is this perturbed Fenchel duality, but I want to show you exactly what the algorithm looks like. The algorithm is going to look very similar to the algorithms that we saw a moment ago, but it's really not one. Instead of, it's a meta algorithm. It's a class of algorithms. So here is the meta algorithm, the components or the ingredients for the meta algorithm. We want to, the meta algorithm is going to apply to the composite minimization problem. And we are going to make the assumption that the proximal mapping is computable. So this proximal mapping is computable as the proximal methods that we mentioned earlier. The key ideas about the meta algorithm is that we generate two main sequences. I'm going to label them S and Y. And at each iteration, we pick some subgradient of F at Y. We pick some step size, and then we update S. I want to note that the update is on S via this proximal mapping. So we take our next S is going to be the previous S minus some step size times this subdifferential that we computed at the kth iteration. Okay, so those are the key ideas. There is going to be some flexibility on how we select the sequence YK. And the flexibility of that YK in some way is what gives the nature of meta algorithm, because different choices of the YK will lead to different algorithms. So here is the meta algorithm, is the algorithm that you see there that again looks fairly similar to the algorithms that I mentioned a little bit earlier, to the proximal gradient, or to the fast proximal gradient, even to the proximal, even to the projected subgradient. So the algorithm is very simple. The initial point is some point S minus 1, right? It is convenient to label S beginning to -1 because of a formula that I'm going to show you in a moment. And then we update S this way. We pick Y. Then we select some G, that is a subgradient of F at Y, some step size. We take S, move negative TK in the direction of that subgradient, and then apply the proximal mapping to get SK. So here is some convenient notation that I'm going to use. Big F, just to lighten up the notation in a few places, big F is going to be the sum of the two terms here, F and psi. And then whenever we have G subdifferential, we will denote df xy, this Bregman distance. We take f of x minus f of y minus g x minus y. That's usually called the Bregman distance in convex optimization. So this is the main theorem, and there is a lot of notation here. So let me try to just walk here slowly. The main key point of the theorem is that this is a formal perturbed Fenchel duality statement. This is a formal perturbed Fenchel duality statement. The left of this inequality is something that is like the duality gap, except that the psi here has a little perturbation decay. The right-hand side essentially is like the delta that I was mentioning earlier. Okay, so let me tell you one thing that is important here is if we look at the algorithm generates sequences Y and S. The theorem concerns these sequences X and U. So what is X and U? X is this ergodic, this average of the SIs, and U is this average of the GIs. Okay, so this kind of averaging, right, is like it's an ergodic kind of a convergence is common in first order methods, and that is very much at the heart of the proof of this theorem. We don't prove something about the main iterates that the algorithm generates, but instead about these averages XK and UK. Now the perturbation here that we need to make on psi, the perturbation is this guy, little dk, which is the Euclidean distance from the initial point square divided by 2 times the sum of all the step sizes. So x0 here, just for convention, the xk's are defined this way for k greater than or equal to 1. For 0, for convenience, we can think of x0 equal to the initial point s minus 1. Now the right-hand side, the second term is easy and simple to understand, but the first term is this difference here. The first term is we take big F. Let me recall, big F was the primal objective. Big F evaluated at, big F evaluated at x plus theta s minus x minus 1 minus theta f of x minus theta f of s. So this first term is less than or equal to 0, and then theta times the Bregman distance. So that is the theorem. The thetas here, the thetas are essentially a transformation of the step sizes t. So t in the algorithm, t is a positive step size. Theta is the kth step divided by the sum of the first k minus 1 steps. So theta and t essentially are like a transformation of each other. All right, so that is the main theorem. And then what I want to do next is show you how the convergence of iconic first order algorithms essentially can be obtained from what I've discussed so far. Before I go there, I want to reiterate something that is maybe central and it's easy to maybe it's easy to get a little overwhelmed by the notation. Let me emphasize a couple of things. This algorithm is extremely generic and makes very weak assumptions about, very minimal assumptions about my problem. All I'm assuming here is that we have this composite problem with f and psi convex, and that we have the proximal mapping for psi. That's all I'm assuming here. And then under that assumption, I obtain this perturbed Fenchel duality theorem. Again, the theorem holds under very general assumptions. So these two statements are extremely general. What I'm going to show next is that if we specialize them a little, then we recover the convergence of the iconic first order methods. And I'm going to emphasize the proximal gradient and fast proximal gradient in particular. So let me recall the proximal gradient. The proximal gradient, this is the same algorithm exactly that I mentioned earlier at the beginning of the talk. The proximal gradient is this kind of update, and I'm using as the name of the main sequence, y, just to make it match my meta algorithm. So the proximal gradient, it turns out to be identical to the meta algorithm if we make this choice of y. If the y, at every iteration, we pick y to be precisely the previous s. So remember that in the meta algorithm, we have two sequences, s and y, and there was some flexibility about how we choose y. So the proximal gradient is the version of the meta algorithm that we obtain by choosing y equal to yk equal to sk minus 1. And the main theorem, again, I'm just reiterating what the statement of the main theorem was, is that the duality, the perturbed duality gap, this term here, is bounded above in terms of this delta k, this whole term on the right-hand side. Now, the more complicated term here is the d. This d is, we are recalling the expression for d here. If I ignore the first three terms, which by convexity, the first three terms are the sum of the first three terms together are less than or equal to 0. So if I ignore those, I get this inequality. The d is less than or equal to theta, the Bregman distance from S to Y. So I get, from the main theorem, I get this inequality. And that immediately gives us this theorem. If we choose our step sizes judiciously, if we choose the t's to be not too large meaning that this inequality holds, then we get that the for any x, the gap between the kth iterate and the objective value at x is less than or equal to this distance of x minus x0 squared divided by the sum of all the step sizes. The proof of this, I want to include it here because it's just a couple of lines. The main theorem implies that the main theorem, which is what I had in the previous page, implies that this term is less than or equal to what I have in the right-hand side. So if the t's are correctly or judiciously chosen, each one of these terms is going to be less than or equal to 0. So we get that this is less than or equal to 0. Okay, and that is exactly what this is going to ensure. So we get that this is less than or equal to 0. And then from here, the perturbed duality, we get that if we take f plus I at xk minus any x, this is less than or equal to dk of x, which is that distance divided by the sum of the t's. So that's the that's essentially the convergence of the proximal gradient. There is this iconic 1/k convergence that we can obtain if we make a little bit more of an assumption of our problem. So suppose that my optimal set is non-empty and the function f is smooth. More precisely, this is called LSmooth. LSmooth means that the Bregman distance is bounded above in terms of the Euclidean distance this way. The smooth component of the problem is LSmooth. The differentiable component is LSmooth when, for example, the gradient of f is L Lipschitz. So if f is LSmooth, then we can take this inequality, guarantees that in the previous theorem, we can take t to be at least 1/L. Okay, that's what we have here. This is at least 1/L. And then from the previous theorem, we get this 1/k convergence. Okay, the kth iterate minus the optimal value is bounded above by L, the distance from the initial point to the optimal solution square divided by 2k. And that follows again by just taking t greater than or equal to 1/L. So that gets us the 1/k convergence. I want to sketch how we get the 1 over k squared convergence, that is the fast proximal gradient. And in some way, this is the part of the most technical part of the talk that I would like to get through, because this is something that is like a holy grail. Many people in my community have been obsessed with trying to find a simple proof of the accelerated first order, the convergence of accelerated first order methods. And that seems to be very evasive. Most of us learned about acceleration. Most of us learned about acceleration many years ago and even teach it to our students. But then whenever we teach that to our students, we often say, this is kind of a mysterious thing. We include this momentum and that somehow does the trick. I want to argue that this is our effort to try to shed some light on that, on why acceleration happens. The next couple of slides are going to show you why acceleration happens. And I think we found a way to explain why acceleration happens. So the fast and proximal gradient, both of those algorithms are going to be based on this a little more elaborate algorithmic scheme. We are going to generate now y and s, where the key is that y is going to be this combination of x and s, the previous s. So it's a convex combination of x and s. S is going to be this prox of s and the step size t times the gradient of f evaluated at yk. And then x is going to be updated this way. We take a combination that looks very similar to the one for y, but there's an important difference here. Here we use the most recently updated sk. And so this is a convex combination of the previous x and the new s. Okay, so that's how we update x. All right, so that's our fast. It's going to be both actually fast and universal proximal gradient. So this again corresponds to a special case of the first order meta algorithm that I mentioned a little bit earlier. This is exactly the first order meta algorithm if we make a very, very particular choice of the sequence y, if we choose y in this fashion. Okay, this is exactly the first order meta algorithm. And a little observation here, I wrote this way because this is going to be convenient for my needs. But the yk, if we play around with the algebra here, can also be written in this other way that sometimes we encounter. This second expression you see here is a little more similar to how we often encounter fast or accelerated first order methods, namely the y includes this kind of momentum term. The second term here is some kind of momentum term on x. So this is again the first order meta algorithm. Is the same meta algorithm we mentioned before. So essentially the same reasoning, identical to the reasoning that I showed for the proximal gradient, regular proximal gradient applies here. Namely, the main theorem gives us this inequality provided, so this gives us this inequality provided that the step sizes are chosen judiciously. So if we choose the step sizes so that this inequality holds, that guarantees that we get our perturbed Fenchel duality with 0 on the right-hand side. And from there, once again, we get this inequality that the objective at the kth iterate minus the objective at any point is less than or equal to dk of x, where dk now is going to be x minus x0 squared divided by the sum of the step sizes. So let me go back just a couple of slides because I want to highlight the incredible resemblance between the proximal gradient and the fast proximal gradient. So the title of this slide here is the convergence of fast proximal gradient. This was the convergence of just regular proximal gradient. The steps here this step and this step are identical. The one difference is that for the proximal gradient, the y is chosen more simply, and we choose the step sizes so that this holds. For the fast proximal gradient, the y is chosen more carefully, and then the step sizes are also chosen a little bit more carefully so that this holds. What does that get us? Well, what that gets us is the following. If we make the same assumption about f, that is, if f is LSmooth on C, that is, if we have this inequality, then in the fast proximal gradient, this requires just a little simple calculation. It can be shown that this d function is less than or equal to L theta square times si minus 1 square. So what this means is that we can take t larger here. So at the end of the day, in the proximal gradient, this denominator grew like t. In the fast proximal gradient, this denominator grows, this denominator in the proximal gradient grew like k, proportional to k. In the fast proximal gradient, this denominator grows like k squared. Essentially, the t's are increasing here, whereas in the proximal gradient, they're not increasing. So we recover, if we have L smoothness, we recover the 1 over k squared iconic convergence of fast proximal gradient, which is this convergence here. All right. So again, there are some key components here. The kind of key essence that I want to highlight is the minor tweak to go from the proximal gradient to the fast proximal gradient is that here there is no difference, but the one difference is that this denominator here can be grows faster for the fast proximal gradient. All right, we can actually push this a little bit farther and go to an algorithm that is called the universal proximal gradient, and that is if we take a more generic type of smoothness. So I like to call this a smoothness-like condition. Suppose that for some nu between 0 and 1, we have this kind of inequality. So the case of regular smoothness is nu equal to 1. If nu is less than 1, is some kind of weak smoothness. So this holds, for example, if the gradient is Holder continuous, is nu Holder continuous, then this inequality holds. And then we have this more general theorem. If we have that smoothness-like condition, which is a little more more generic, and the step sizes are chosen a little bit more carefully, the step sizes are chosen like this, then the suboptimality gap, or the difference between the objective value at xk and any other point, is bounded above in terms of what you see on the right-hand side. So it just, the expression for is subgradient, is sublinear on k, but the exponent now is a little more complicated here. So again, when nu is equal to 1, we get k squared, which is the speed of the accelerated or the fast proximal gradient. Otherwise, we get something that is a little less than 2 here in the exponent. And the proof is very similar to the proof where we saw before. The only difference is that there is an extra epsilon here, but we get a very similar argument to what we had before. And then this gives us this kind of universal convergence that was first proposed by Nesterov in a math programming paper, in a seminal math programming paper a few years ago, that if we have nu smoothness, then we have this kind of 1 over k, 1 plus 3 nu over 2. So again, nu equal to 1 corresponds to the nu equal to 1 corresponds to the k square acceleration. Nu less than 1 corresponds to something that is a little bit weaker. All right, so let's see, I have about 10 more minutes. So let me switch to something that is non-Euclidean, because this is kind of cool. It's a bit more versatile, a bit more general. So the first order meta algorithm that I mentioned before, sometimes it's called the Euclidean meta algorithm. I'll show you why. The Euclidean Bregman proximal algorithm. We call this the first order meta algorithm non-Euclidean because it's based on a certain non-Euclidean distance. So the key ingredient here is to use a Bregman distance, a Bregman reference distance. So we again want to solve the same problem that we had before, but this time we are going to assume that the proximal mapping that is computable is a mapping of this form. So we do not necessarily have an Euclidean term here. Instead, we have some Bregman distance here. So H is some reference function, and DH is the Bregman distance generated by H. So it's this function. So in the case when we have the Euclidean, when H is the Euclidean norm squared, the Bregman distance is y minus x squared divided by 2. And this proximal mapping is exactly the one that I mentioned before, okay, in the Euclidean version of the first order meta algorithm. This is a more versatile one because the H in principle could be a more general reference function. So there's a nice advantage of dealing with the non-Euclidean. So first of all, the first order meta algorithm has a completely straightforward extension. This is basically a copy and paste of the algorithm that I had before. So the first order meta algorithm can, without any effort, be stated in non-Euclidean terms. And why would we want non-Euclidean algorithms? Why would we want a non-Euclidean reference function? Well, because this just adds a great deal of extra flexibility. For example, this is something that probably some of you are familiar with. If we are interested in optimizing over the simplex, over the standard simplex, then this proximal mapping is easier to compute if we use the entropy function as the reference function. It's easier than if we use the Euclidean distance. The Euclidean distance, this is doable, but for the entropy, this is actually easier. So that's the merit of using non-Euclidean algorithms. The main theorem that I mentioned before essentially has a very, very similar version here in the non-Euclidean context. It's practically the same theorem. So this is almost like a copy and paste what I did earlier. The left-hand side is the perturbed Fenchel duality left-hand side, and the right-hand side is a certain term here that depends on the same kind of D function. And instead of the Euclidean difference here, the Euclidean norm of Si minus Si minus 1, we have the Bregman distance. Okay, that's the only difference there. So we have essentially the same kind of statements that we had before. So some special cases of this first order meta algorithm, the non-Euclidean one, we have a Bregman proximal gradient, non-Euclidean one. We can get 1/k convergence if we have this kind of smoothness assumption now. This is what sometimes some authors call the relative smoothness assumption. So this is a smoothness assumption between f and the reference function h. This is very nice because sometimes you could have a function f that is not necessarily, the gradient is not necessarily Lipschitz, and therefore the function is not necessarily LSmooth in the classical sense, but it could be in this more broader sense if we choose the reference function accordingly. So we get, if this happens, this is called relative LSmoothness, then we get 1/k convergence. This was a very nice development that was by Bauschke, Bolt and Teboul, and also by Liu, Freund, and Nesterov. And it was both of them did it independently and very close to each other. We also have some version of fast and universal Bregman proximal gradient that essentially gives us the same kind of statements that we had before, a faster rate of convergence, provided that we have some smoothness-like property. So the smoothness-like property is something sort of like what I mentioned earlier. There is also something about the non-Euclidean case that is interesting, and that is a nice connection with the conditional gradient algorithm. So I just have a few minutes. Let me try to squeeze this part about conditional gradient because I find it to be interesting, and because it's something that I have very, very recently, literally in the last couple of weeks, I've been working on. So this is the conditional gradient algorithm in a slightly more general form. So this is conditional gradient, not for a constraint problem, but for the composite problem. Okay, so the conditional gradient is based on this assumption. We compute the gradient, and we then compute this minimizer S, where we minimize the linear term defined by the gradient and the term psi of S. Okay, so this is S, and then we move from the current point, take a convex combination from the current point and that S. So it turns out that this is exactly our first order meta algorithm for a very special choice of reference function. If we take the reference function to be identically equal to 0, then this guy here is just this kind of trivialized proximal mapping for that very particular case, for that reference function equal to 0. So we get the conditional gradient. So our main theorem from before also applies here, and we just get a simpler version of our main theorem. The main theorem in this case, in the conditional gradient, has a much simpler expression. We have this kind of duality gap. In this case, the duality gap here is not perturbed. There is no need to perturb psi. And on the right-hand side, we get this expression where the d here is something a little bit simpler. The d is the Bregman distance of f at this point from x, and this difference of psi. So if we have this curvature condition, this is kind of like a relative smoothness, or is related to the concept of curvature that Jagi proposed a few years ago. If we have this kind of curvature condition, this is what is going to get us the convergence of the conditional gradient. So this curvature condition in particular holds if the domain of psi is bounded and if the gradient is Holder continuous. So if that curvature condition holds, then we get this kind of convergence for the conditional gradient, which is a little more general than the textbook, the classical 1/k convergence of the conditional gradient. There is something that I did that I've been working on just for the last couple of weeks. So I am going to indulge myself in the last couple of minutes. This is maybe going a little far, but I'm going to take the chance with you guys since I have you here. This actually can be pushed a little bit further. This is something that I got inspired to do from some recent work by several sets of authors that show that the conditional gradient actually can have a rate of convergence that ranges from sublinear all the way to linear, depending on how much we assume about the components of the problem. So I realized that what is key for obtaining that spectrum of convergence rates is to think a little bit more broadly about this curvature condition. So this curvature condition here, we can extend it to this more general curvature-like condition that I propose here. So here, this is very similar to the formula that I showed just a moment ago, except that we have this extra term here, gap xg to the r. So what is gap? Gap is just the duality gap. And gap xg is the duality gap between x and its gradient. Okay. So the previous curvature condition just corresponds to the special case when r is equal to 0, because in that case, this term just becomes 1. The special case when nu is equal to 1 and r is equal to 1, when both of these guys are equal to 1, that corresponds to the case when the gradient of f is Lipschitz continuous and psi is strongly continuous. And this is a very special case. I'll show you why. So this is kind of the key theorem. The key theorem is that if we look at the best duality gap that the conditional gradient achieves in the first k iterations, depending on how well the curvature condition holds, we can have a convergence that goes from linear, in the best case, when r is equal to 1, this is linear, to sublinear. If r is less than 1, then the convergence is basically sublinear, is what you see here. Even when r is less than 1, something interesting happens for the conditional gradient, and that is that initially for the first few iterations, we have some linear convergence, and eventually, after crossing a threshold, we have sublinear convergence. So that is a much stronger collection of convergence rates for the conditional gradient based on this much broader curvature-like condition. All right, so I think I have already, I'm nearly exhausted my time. Let me reiterate, in case I lost you, which is, I realize is not unlikely. Let me reiterate the main idea here, right? We consider this problem where f and psi is convex, okay? The composite convex minimization problem, a very, very pervasive problem in convex optimization. The gist of my story is that essentially a large collection of first order methods, a whole meta algorithm that contains the most popular first order methods, generates sequences that satisfy this perturbed Fenchel duality property. And from there, we can, with relatively little effort, derive the convergence rates of all of them, of all of the conditional gradient, Bregman proximal gradient, Bregman fast proximal gradient. Something that I didn't discuss because I realized I was not going to have time is subgradient. All of them can be, all of them encompassed in terms of the first order meta algorithm and this perturbed Fenchel duality, essentially this one line that I'm highlighting there. The main reference here for what I have presented today is this paper that is a joint work with David. And another short paper that I'm hoping to release maybe in the next couple of days is this type, I'm giving it this title tentatively, a fine invariant convergence rates of the conditional gradient method. The business of affining gradient, if you are curious, is certainly something that I would love to talk more. I could talk about it for hours. So if we have absolutely no other topic, I'll be more than happy to talk about affining variance right away in our discussion session. But I think I should stop there for now. Thank you. Thank you so much for your attention. Thank you, Vera, for chairing the session.
Thank you very much, Javier, for the very interesting talk. So just quick explanations that I'm going to stop recording now. So in the discussion session, we could be very free, to discuss things and maybe something that could be almost a research idea. I'm just going to stop recording now, and then we'll start, discussing things and asking questions.